Everybody, welcome back. Today we're going to look at LeetCode 226. It's another LeetCode easy working on tree node objects or binary trees. And this is kind of a famous problem actually. There used to be some trivia, I think down here somewhere, that had to do with this famous engineer who wrote Homebrew. If any of you have installed software on Mac with Homebrew, you'll know what that is. And I think he interviewed at Google and couldn't do this problem. I think this was maybe before everybody kind of knew that you had to do these data structure and algorithm problems. And I think he failed it. So kind of funny note. It used to be on here. I think they've since removed it, or I don't know, maybe you got to pay for premium to get it. I'm not sure. Pretty straightforward problem. So what does it mean to invert a binary tree? It really means to rotate this around the vertical axis, as you can see. So left nodes turn into right nodes, and right nodes turn into left nodes. They've got some good examples here. And one important thing is that when we write this program, we're going to have to return the root. So that's going to affect some of the return statements in our functions. So we can't just move the pointers. We actually have to move all the pointers and then return the root object itself. Anyway, let's hop into some code and take a closer look at that. Okay, I've got some code pulled up here for us to look at. Note that this is the code that comes from LeetCode right here. And then this is an extra method, two methods really, that I've kind of butchered from this Stack Overflow post. Go read the post if you're curious about the source of a lot of this. This code right here, these two extra methods that allow us to print a tree node object out layer by layer with a tiny bit of formatting. But these are not important or central to solving the problem at all. You wouldn't be expected to do this for this problem, and you don't need it. I just like it because I like to visualize my problems. Literally, I like to print them out and look at them and inspect them. And without this, it's kind of hard to do that. So, I mean, I can give you a quick overview of this, but I don't want to focus on it because it's not core to the problem. And the other thing is that there's some kind of mid-level Python stuff going on here. We've got doubly ended queues. We've got an inner function. We're using generators and list comprehensions. And these are all pretty straightforward things once you practice them, but they're a little tricky learning first time, and they're not important to this video. Just know that if you want to kind of do this in your own environment and print out the tree node objects, you can copy this code and then just call this method print by layer. And it should work just fine for you. Okay, so today I really want to show you two different solutions, and I'm going to call them reverse. Let's call it reverse long. And then later I want to cover something called reverse simple. All right, so I've commented out the simple function below, and we're going to work on the long one. And what I want to do is I want to go through this and write down code comments about roughly what we have to do to reverse all of the pointers in this binary tree. So the first thing that we often have to do with any kind of recursive algorithm is we need to do some kind of null check at the top. So those are easy to forget. I'm just going to write that up there at the top there. We really need to just make sure that the input is a tree node. If it isn't, we want to return none, right? Because a lot of times these recursive algorithms, they bottom out and there's nothing left, and you got to go back up the stack after that. Okay, so we need to do a null check, and then also we need to. I want to work left to right, so I want to make the left pointer equal to the right pointer and the right pointer equal to the left. It doesn't matter which one you do as long as you are consistent with the order. But to make things kind of simpler, I want to go left to right. I think that's a little bit more natural for people who, write left to right. Maybe if you write Arabic and you're watching this, maybe go it the other way. Unproven theory of mine, but maybe that'll work easier for you. Okay. So we need to do a null check. What else do we want to do? Well, I mean, we got to do what I just said, right? We want to take the left pointer and assign it to the right pointer. And then basically we want to do the same thing here, but we want to do it for the right pointer. And then we've got a recurse. So we got to move to the next level basically. And then, that new function call will do it all again. And then we have to think about what we want our return to be here. Right now I'm going to leave this empty because that's kind of a special point I want to focus on. I think we can actually get this to work without returning anything, but I think in order to write the kind of function that LeetCode is expecting, we will need to have a return object down here at the bottom. I guess while we're here also, we can define our input, so we can call this a root because it's kind of the starting position of a tree. We should always have, some tree or subtree will be at, the starting position of that, the root node of that tree. All right, now we can just go through and try and write some code for what these code comments are asking us to do. So an L check is easy enough. We can check if we don't have a root object. So if we don't have a root object, well, let's go ahead and return none. Okay, yeah, simple enough. And then we want to take our left pointer and assign it to our right pointer. So whatever is in root.left, assign that to whatever is in root.right. Okay, easy enough. And then we want to do the same thing for our right pointer. So root.right is equal to, well, okay, here we have a problem. We want to assign really like whatever was in root.left, but like obviously we don't have that option right here. So because what we had in root.left was now overwritten with whatever is in the right pointer, we really need to create a copy of what was in left so that we can access it after we overwrite it. So I'm going to create a variable called copy, which is really just a pointer to whatever the left pointer was pointing at. And then down here, we can take our right pointer and assign it to, what was in copy. And then finally, we've just got to keep this algorithm going. So we need a reverse long call on everything to the left, and then we need a reverse long call on everything to the right. And I think actually this is enough code. Well, we need to uncomment return so that our function knows when it's done. I think this right here will actually reverse our tree nodes for us as we have it. Okay, now that we've got this function in memory, let's go ahead and just write a simple test case and see what the output looks like. So we can call this test. There's probably a lot better names for it, but I'm just going to call it test for right now because I just want to view the output. And what we want to do is we want to call reverse long on 7, which I've defined up here. And then we want to access the print by layer method, which is part of 7. And we can just inspect the results real quick and make sure they look the way we're expecting them to. And sure enough, 5 and 6 are still the children of 7, but they've swapped. And then 1 and 2 are still the children of 5, and 3 and 4 are the children of 6, but they have switched places. So that's good. And the next thing we want to do here is I want to change this so that we can get rid of this copy notation. So there's nothing wrong with this. It works perfectly fine, as you can see here. And if I added return root here and put this in the LeetCode, it would submit and it would pass. However, one of the great things about Python is that it has such good notation that a lot of things like this that are useful in a lower level programming language and really speed things up aren't sped up by doing this manually. And so instead, we can use tuple notation. So we can use commas on left and right hand sides of the equation symbol, the equal symbol, sorry. And we can do all of this really. I think we can take these 5 lines and condense them down into, into 2 lines. So we can handle the recursive calls, and we can internally create this copy variable all in one step. So yeah, I'd like to show you that next. So we can write this simple version of reverse now, as long as we define it. So we're going to define reverse simple. The bookends are going to be the same. So we still want root as our input, and then we want to make sure that We actually got an input. And again, we want to return the root object so that LeetCode, when it parses our solution, gets the right object for the checker. But the key difference here is that one, like I was saying before, we're going to allow Python to handle the copying functionality. We're going to let it do that internally. We don't have to manage that variable ourselves. And then actually, we're going to allow our left and our right sides to be updated simultaneously. And syntactically, all we really have to do is just add a comma. Well, what's going on under the hood is Python's doing something called tuple unpacking, and it's pretty interesting to read about. I'm not going to go into too much depth here. But really, all we've got to do is write a comma. And what do I mean by that? So basically, we can do what we were doing before. We can switch the places of root, the left pointer and the right pointer. And we can fold in the recursive calls all into one line. So everything we do on the left side of this comma, we need to do also on the left side of the comma on the equal sign over here. So we want the left pointer now to point to the outcome of the recursive call here on well, simple reverse, can't forget that, simple reverse of whatever is on the right, and then the same idea over here, but everything that is on the left. And notice there's no copy variable now. So what we have on the left, turn it into whatever the outcome of reversing is on the right, whatever we have on the right, turn into whatever we have as the outcome of the reverse on the left. And just like before now, I just want to make sure that the outcome looks correct. So I'm just going to overwrite the old test variable and call reverse simple on 7. And then again, access the print by layer method on 7 and check out the result. Before we do this, let's go ahead and redefine 7 because 7 is probably reversed in memory from when we called it earlier. And then let's put this function in memory and test the output. And boom, yeah, it looks like the other function that we wrote. Okay, so as promised, I've gone ahead and run these in the LeetCode environment. And I got a bit of a surprise. You'll notice that the longer bit of code we wrote, the more verbose code, is very efficient. It would be hard to beat this. And in fact, our more elegant code does not beat that in terms of performance. In the LeetCode environment, this prettier block of code is actually much less efficient. By the way, if you think the code has changed a little bit, it's just that our solution class here, we're using a method, whereas before we had a tree node class and I just wrote a generic function on it. So we have these self calls since we don't have an inner function inside invert tree. I hope that's kind of review and simple for people, but if it's not, that's why we're seeing self here. It's because we're calling a method in a class instead of just a function in the global environment. I was surprised by this, so maybe in an interview, this is the code you write. I'm not really sure. I'd love to learn why this is more efficient. So if any of you know, please leave a comment and you can teach me something. Besides that, that is all I've got for the video today. So I hope you guys have all learned something, and I'll catch you next time with a new algorithm.